ancient amber together to managing high-voltage grids that power entire continents. For 2,500 years, we have been trying to protect ourselves from the same force that lightning uses to destroy. From Thales' first observation of a strange attractive force in fossilized resin to Tesla's modern revolution of alternating current, we trace the lethal, invisible evolution of electricity, a force that was once dismissed as a curiosity, and is now the silent pulse of global civilization. The amber that Thales rubbed against wool produced a spark too weak to feel. The transmission lines that cross continents in 2026 carry voltages that can vaporize a human body in microseconds. Between those two extremes lies one of the most dangerous and most essential engineering journeys in human history, the journey to capture, stabilize, and distribute the most volatile form of energy on Earth. Imagine a force so unpredictable it was once considered magic, and is now the silent pulse of our global civilization. From primitive insulators that failed catastrophically to massive transformers that step voltage up and down, across thousands of kilometers, the journey to stabilize electrical distribution was filled with danger and genius in equal measure. Engineers were working with a force they could not see, could not fully predict, and that killed without warning when the engineering failed. Discover how engineers tamed this spark and built the world you see today. A world in which a force that once arrived only as terrifying, destructive lightning now flows silently through walls, under streets, and across oceans, controlled to within fractions of a volt. 2,500 years ago, this story began with a curious observation about static energy. Today, it has become the vast and complex infrastructure of 2026. This is the story of how we took control of an erratic energy source to define modern existence. From Thales' amber to Tesla's alternating current, from Edison's direct current battles to the synchronized regional grids that keep hospitals running and cities lit. This is the relentless effort to capture, distribute, and control the most dangerous energy on the planet, and the story of what happens when, for even a fraction of a second, that control fails. Around 600 BC, the Greek philosopher Thales of Miletus observed that amber, fossilized tree resin, when rubbed with fur or wool, would attract lightweight objects such as feathers and straw. He had discovered what we now call the triboelectric effect, the transfer of electrons between two materials in contact, leaving one material with a surplus of electrons and a negative charge, and the other with a deficit and a positive charge. The resulting charge imbalance creates an electric field strong enough to attract neutral objects. Through induced polarization, Thales had no concept of electrons, charge, or fields. He had an observation. Friction on amber produces an invisible attractive force, and he recorded it as a curiosity of natural philosophy. For the following 2,000 years, this remained essentially all that anyone knew about electricity. It was a parlor trick, a demonstration of a strange property of certain materials, entirely disconnected from any practical application. The Greek word for amber, electron, would eventually give the phenomenon its modern name, but the gap between naming a curiosity and harnessing a force would take 2 millennia to close. The 18th century transformed electricity from a curiosity into a subject of systematic experimentation, but still not a usable energy source. The Leyden jar, invented independently around 1745 by Ewald Georg von Kleist and Peter von Muschenbroek, was the first device capable of storing an electric charge for later use. A glass jar lined inside and outside with metal foil, with a metal rod passing through the lid to contact the inner foil. The Leyden jar functioned as what we would now call a capacitor, storing charge on one foil layer while the glass dielectric prevented it from immediately discharging to the other. Experimenters could charge a Leyden jar using a friction generator, a rotating glass globe rubbed continuously by hand or leather pads, and then discharge it through their own bodies, through animals, or through wires, observing the spark and the physiological shock. Benjamin Franklin's famous kite experiment of 1752 was an attempt to demonstrate that lightning was the same phenomenon as the static electricity being studied in laboratories, that the terrifying destructive force of a thunderstorm and the curious spark from a rubbed amber rod were, fundamentally, the same thing at different scales. Franklin's lightning rod, a grounded metal conductor mounted above a building to intercept lightning strikes and conduct them safely to ground, was the first practical engineering application of electrical science, and it remains in use, essentially unchanged in principle, in 2026. For 2,500 years, electricity remained a phenomenon to be observed, occasionally demonstrated, and in the case of lightning, feared and crudely managed. It was not yet a force that could be generated on demand, stored in useful quantities, or transmitted from where it was produced to where it was needed. That transformation would require an entirely different kind of engineering, and it would happen with extraordinary speed once it began. Thomas Edison's direct current electrical distribution system, demonstrated commercially at the Pearl Street Station in New York in 1882, was the first practical electrical grid, generating direct current at a central station and distributing it through underground copper conductors to customers within approximately 1 mile of the generating station. The 1-mile limit was not arbitrary. Direct current cannot be efficiently transformed to higher voltages for transmission and then back down to safe voltages for use. The voltage at which DC is generated is essentially the voltage at which it must be distributed and used, and at the voltages safe for direct customer use. The current required to deliver useful power over distance produces resistive losses that become prohibitive within roughly a mile. Edison's system worked, but it could never scale beyond a dense urban core surrounding each generating station. Every neighborhood would need its own power plant. Nikola Tesla's alternating current system, commercialized through George Westinghouse's company, in direct competition with Edison, through the late 1880s and 1890s, solved the scale problem through a single critical capability: the transformer. A transformer can efficiently step alternating current voltage up or down, with the relationship between input and output voltage determined simply by the ratio of windings in the transformer's two coils. This meant that AC power could be generated at a moderate voltage, stepped up to a very high voltage for transmission, minimizing resistive losses. Over long distances, since power loss is proportional to the square of current and inversely proportional to voltage, and then stepped back down to safe levels at the point of use. The war of the currents was fought as much through public perception as through engineering. Edison's side conducted public demonstrations of AC's lethality, including the electrocution of animals, to argue that AC was too dangerous for public distribution. But the engineering advantage of AC was decisive, and by the early 20th century, AC had become the standard for electrical distribution worldwide. The early electrical infrastructure built during this period was extraordinarily dangerous by modern standards. Bare or minimally insulated wires were strung on wooden poles through city streets, often alongside telegraph and telephone wires, with no standardization of voltage, no systematic grounding, and frequent fires and electrocutions resulting from the chaotic proliferation of overhead wiring. The transition from isolated local power plants, each serving a single factory, neighborhood, or building, to synchronized regional grids was driven by a fundamental economic and engineering insight. Electrical demand varies enormously by time of day and by customer type, and a grid serving a diverse mix of customers across a wide area can be supplied by generating capacity sized for the combined peak demand, which is significantly less than the sum of each customer's individual peak demand. Synchronizing multiple generating stations to operate at the same frequency and phase so that their output could be combined on a shared transmission network required precise mechanical governors on generator turbines, and eventually, automated frequency control systems, the beginning of grid-scale control engineering. The high-voltage transmission line is, in engineering terms, a long conductor carrying lethal voltage suspended in open air above the ground, supported by structures that must prevent that voltage from finding any path to ground other than through the intended circuit. The insulator, the component that physically supports the conductor while electrically isolating it from the grounded tower structure, is therefore one of the most safety-critical components in the entire electrical system, and its development through the 20th century represents a continuous battle against the physics of dielectric breakdown, contamination, and mechanical failure. Early insulators were made of porcelain, a ceramic material with excellent dielectric properties when clean and dry, but whose performance degrades severely when contaminated with dust, salt, or moisture, which create a conductive path across the insulator surface that can lead to flashover, a sudden electrical discharge across the insulator that can damage equipment and interrupt transmission. The characteristic bell or disc shape of porcelain insulators, with multiple ribs and sheds, is a direct engineering response to this problem. The shape maximizes the surface creepage distance, the path length that a contaminating film would need to bridge, while the underside ribs remain dry even in rain, maintaining a dry section of the leakage path that resists flashover. The transformer is the device that makes long-distance transmission possible, and its engineering challenges scale dramatically with the voltages and powers involved in modern grids. A large transmission transformer may handle hundreds of megawatts at voltages of 500 kilovolts or more, and the engineering challenges at this scale include not just electrical insulation but also the attachment of enormous quantities of waste heat generated by resistive losses in the windings, by eddy currents and hysteresis losses in the iron core. Large transformers are typically immersed in mineral oil, which serves simultaneously as an electrical insulator. Oil has a higher dielectric strength than air, and as a cooling medium, circulating through external radiators to dissipate heat. The failure of a large transmission transformer is among the most consequential single-point failures in an electrical grid. These devices are custom manufactured, require months to replace, and their unavailability can leave an entire region without the transmission capacity needed to meet demand. The development of mechanical load-tap changing transformers, which can adjust their voltage ratio while energized by mechanically switching between different winding configurations, gave grid operators the ability to maintain voltage within acceptable limits, despite varying load conditions, without interrupting power delivery. This represented the beginning of active, dynamic grid control, moving beyond the passive infrastructure of wires, insulators, and fixed-ratio transformers toward a system that could respond to changing conditions in real time, a capability that would become essential as grids grew larger, more interconnected, and more dependent on precise voltage and frequency control to maintain stability across enormous geographic areas. The ultra-high voltage transmission lines that cross continents in 2026, operating at 800 kilovolts and above for the longest direct current links, and at 500 to 765 kilovolts for major alternating current corridors, represent the physical backbone that allows electricity generated in one region to be consumed thousands of kilometers away, enabling the geographic diversification of generation sources that is essential to modern grid reliability and, increasingly, to the integration of renewable energy. High-voltage direct current transmission, which had been technically understood since the early 20th century, but was impractical at scale until the development of high-power semiconductor devices in the late 20th century, offers significant advantages for very long-distance transmission, lower losses than AC at equivalent voltage for distances beyond a few hundred kilometers, and the ability to connect grids operating at different frequencies, or that are not synchronized, since AVGDC links convert AC to DC at one end back to AC at the other, with no requirement for phase synchronization between the two AC systems. The physical infrastructure of many developed world electrical grids, particularly in North America and Europe, was substantially built in the decades following World War II, and by 2026, large portions of this infrastructure are operating well beyond their original design life. Aging transformers, deteriorating insulator strings, and transmission towers built to load standards that did not anticipate the increased frequency and severity of extreme weather events driven by climate change represent a systemic vulnerability. A single severe weather event can cause cascading failures across interconnected systems, as occurred in several major blackouts of the early 21st century. The integration of variable renewable energy sources, wind and solar generation, whose output varies with weather conditions on timescales from seconds to seasons, in contrast to the controllable output of fossil fuel and nuclear generation, has fundamentally changed the engineering challenge of grid operation. A grid that was designed around the assumption of dispatchable, predictable generation matched to predictable demand must now manage generation that can change output by significant fractions within minutes due to a passing cloud or a wind gust. This has driven the development of grid-scale energy storage, demand response systems that can adjust consumption in response to grid conditions, and increasingly sophisticated forecasting and control systems that must balance supply and demand on timescales and with a degree of uncertainty that the original architects of the synchronized grid in the early 20th century never had to consider. Solid-state transformers, devices that perform voltage conversion using power electronic switching rather than the electromagnetic induction of conventional wound transformers, represent a potential transformation in grid architecture as significant as Tesla's original alternating current insight. Unlike conventional transformers, which have a fixed voltage ratio determined by their winding configuration and operate only on alternate current, solid-state transformers can convert between AC and DC, adjust voltage ratios dynamically without mechanical switching, and provide near-instantaneous control over power flow direction and magnitude. As of 2026, solid-state transformers remain more expensive and less mature than conventional transformers for the highest power applications, but they are increasingly deployed in applications requiring rapid, precise control, including the interfaces between renewable generation, energy storage, and the grid, where the ability to instantly redirect power flow in response to changing conditions provides value that conventional transformers cannot. Artificial intelligence applied to grid management addresses a problem that has grown beyond the capacity of traditional control approaches. A modern grid with millions of individual generation and consumption points, including rooftop solar installations, electric vehicle chargers, and grid-scale batteries, each capable of either consuming or supplying power depending on conditions, presents an optimization problem of a scale and complexity that exceeds what deterministic control algorithms can handle in real time. Machine learning systems trained on grid behavior can forecast demand and renewable generation with greater accuracy than traditional statistical methods, identify emerging instabilities before they become critical, and coordinate the dispatch of distributed resources, batteries, demand response, and flexible generation, to maintain grid balance with a responsiveness that approaches the second-by-second variability of renewable generation. The microgrid, a localized grid that can operate independently of or in coordination with the main utility grid, represents a fundamental shift in grid architecture from the centralized model that has dominated since Edison's Pearl Street station. A microgrid serving a community, campus, or industrial facility with its own generation, storage, and the ability to disconnect from the main grid during a disturbance and continue operating independently, known as islanding, provides resilience against the cascading failures that can propagate across a large interconnected grid. The proliferation of microgrids does not eliminate the need for the high-voltage transmission backbone. Large-scale generation resources, particularly renewable generation concentrated in geographically favorable locations, still require long-distance transmission to reach population centers, but it represents a layering of decentralized resilience on top of Centralized infrastructure, an architecture that the engineers of the early 20th century, building toward ever larger centralized systems, could not have anticipated. 2,500 years ago, a Greek philosopher noticed that a piece of fossilized resin, rubbed with wool, could attract a feather. Today, that same fundamental force, the movement of electrons, flows through a global infrastructure of such scale and complexity that no single person fully comprehends it. An infrastructure that is, in the most literal sense, the life support system of modern civilization. The spark has been tamed. It has not been made safe. It has been made essential. And the engineering of taming it continues, because the alternative is unthinkable.